Okay, so we've been given this question. The question says the wavelength associated with a moving particle depends on its mass, velocity, and the Planck's constant, which is measured in kilograms square meter per second. Show dimensionally that lambda is inversely proportional to Planck's constant over mass times velocity. So here this one is a dimension analysis, so we're going to look onto how we're going to solve it. So here we're going to write the data that we have. We have the Planck's constant, we have the mass, we also have the velocity. Then we are supposed to show that the wavelength is inversely proportional to this using a dimension analysis. So according to dimension analysis, we can solve this question using dimension analysis techniques, because according to dimension analysis they are on depending on mass, which is in kilogram, but according to dimension analysis is denoted by capital letter M, and then the displacement is denoted by letter L, and also the time is denoted by capital letter T. And we know that lambda is a wavelength, and then you know that wavelength it's more like distance or rather displacement. So according to dimension analysis it is denoted by capital letter L. So this is how the lambda or rather the wavelength is denoted. So according to the question, the wavelength depends on mass, velocity, and also the Planck's constant. And we've been told to show by dimension analysis that the wavelength is of Planck's constant over mass times velocity. So this is how we're supposed to show at the end of the day to the given question above. So first thing first, you're supposed to write the relationship on how these physical quantities were depending on. So the first thing first, you know that wavelength was depending on a constant of mass, velocity, and also Planck's constant. So we're going to give relationships to the right hand side of their exponentials. So we're going to name like mass as A, velocity as B, and the Planck's constant as C. So these are the relationships that we are going to use to calculate, or rather to show how this relationship goes about, because we are trying to show how, according to dimension analysis, on how we are going to go about that proven answer there. So according to dimension analysis, this is how we are going to denote all the relationship dimensionally. So you know that on the left hand side there are some physical quantities which are hidden. You know that any number raised to the power 0 is 1. Then like for the wavelength, you know that it's a length. So length is raised to the power 1 because we are trying to make this relationship to be of the same, like from the right hand side and also to the left hand side. So this is how the relationship they are supposed to be aligned with according to dimension analysis. So this one is the principle of homogeneity we are using here. So here we're going to find the values of these exponentials we've made as assumptions, like from our right hand side here for mass for m. So we're going to equate them according to their like terms, according to their relationships. So like from our left, or rather our right hand side, we have mass raised to the power a plus c, and then to our left hand side we have mass raised to the power 0. So this one, the relationship, we're going to use the exponentials as the relationship. So here we're going to have a plus b is equal to 0 as our first equation. So this one becomes our first equation. Second equation becomes L to the power 1 being equal to L to the power 2c plus b. So according to their relationship, we have 2c plus b being equal to 1. This one becomes our second equation. So our last equation for time, so from the left hand side we have t raised to the power 0 being equal to t raised to the power negative b minus b. So according to their relationship, so have negative b minus c being equal to 0. So we're supposed to find the values of a, b, and c from these three equations that we've come up with. So for our third equation, we know that negative b minus c is just the same as negative b is equal to c. So negative b is just the same as equal to c, or c is equal to negative b. So we know now like the relationship on how these are going on. Since we know that our second equation was 2c plus b being equal to 0, and then we know that our relationship for t, which is negative b being equal to c. So we are going to substitute where there is c, we're going to substitute negative b. So we're going to say 2 on negative b there plus b being equal to 0. Oh sorry, here it's supposed to be equal to 1. Here it's supposed to be equal to 1, not 0 but equal to 1, because this relationship came from the displacement L. So this one is supposed to be 1. So next we are going to have our negative b being equal to 1. You know that over negative 1 over negative 1, whereby b, you know, that becomes negative 1. So here we've already found like two numbers that represents like the coefficients of a, or rather the coefficients of b and c. So the coefficients of b and c, we found that it's negative 1. So b is equal to negative 1 and c is equal to negative 1. Since our first equation was a plus c is equal to 0, so we're going to make a the subject of the formula here. You know that a is equal to negative c. Then you know that the value of c is equal to negative 1. So we're going to substitute this negative 1 there where there is c. So we're going to have a being equal to negative of negative. So our a becomes positive 1. So this is how you're supposed to find the coefficients of A, B, and C. Yeah, so we're going to substitute now back to the question. So like from the relationship made so far, so we're going to substitute like wavelength being equal to the constant, mass raised to the power A, velocity raised to the power B, and Planck's constant raised to the power C. So here we're going to substitute now the values that we found. You know that for mass A, we found that it is raised to the power -1, and you know that velocity raised to the power BB is raised to the power -1 as well, and then HC, the value of C is +1. Okay, so by concluding this question, this is how we're going to go about it. So the question can be concluded like this. Where K, any value which is constant according to dimension analysis, is equal to 1. So lambda is equal to Planck's constant over mass times velocity, hence shown